Good morning, dear students. Next we can go through the kinetics of hydrogen-bromine reaction. Kinetics of hydrogen-bromine reaction. We had seen kinetics of hydrogen-chlorine reaction. No. So next is the kinetics of hydrogen-bromine reaction. So here the reaction which is happening in between hydrogen and bromine, that is H2 plus Br2 in presence of sunlight or in the expense of a photon, it will be reacting to form 2HBr. Okay. So here two processes are going on. The first is called as the primary process and the second one, that is the secondary process. Okay. So primary process and a secondary process. So in the primary process, this bromine, it will be absorbing one quantum of energy or one photon. Okay. So bromine, it will be absorbing one photon to give two bromine free radical. Okay. So this is the primary process and let it be equation number 1. Then the next one, that is the secondary process. Secondary process. So in the primary process, the bromine free radicals is formed, which is the initiator of that particular reaction. So this bromine free radical will act as the initiator for that particular reaction. Okay. Then in the second reaction, that is in the secondary process, one of this bromine free radical, it will be reacting with hydrogen molecule. Okay. To form what happens, H2. It is a single bond, isn't it? A single bond H. That means here homolytic fission, and one of the electron, while the bond breaks, one of the electron will be moving to one hydrogen atom and the second electron will be moving to the next hydrogen atom. Okay. So that each hydrogen atoms will be having one free radical. Okay. So one hydrogen, so hereby two hydrogen free radicals are formed. So one of the hydrogen free radical, it will be combining with this bromine radical, okay, to form HBr. And the remaining one will be one hydrogen free radical, okay. So that is the second reaction. Then the third reaction, that is this hydrogen free radical, it will be again combining with the bromine molecule, okay, to form again HBr, and the remaining one will be bromine radical, isn't it? Again bromine radical. So that is the third reaction. Then the fourth reaction, again this hydrogen radical will be combining with HBr. Okay, hydrogen radical will be combining with HBr to form hydrogen molecule plus bromine radical. Okay, hydrogen plus hydrogen radical gives HBr plus a bromine radical. So that is the fourth step. Then the fifth step is that, see here one bromine radical is there. Again one more bromine radical. Both of them combines together to form a bromine molecule. Okay. So this is the secondary process and this is the primary process. That is the reaction. The step 1 is the primary process and the reactions from 2 to 5, that is the secondary process. Okay. And also again we can go through these reactions. See the reaction 2. Reaction 2 means Br radical plus H2 giving HBr plus H. That reaction, it is that particular reaction, it is highly endothermic. That means heat is absorbed. It is a highly endothermic reaction, and also the reaction will be very slow, extremely slow at ordinary temperatures. The reaction will be extremely slow at ordinary temperature. So that is a peculiarity of the second reaction or the second step. Then coming to the fourth reaction, see H dot plus HBr giving H2 plus Br dot. See, is there any relation connecting this second reaction and fourth reaction? See, this fourth reaction is just the reverse of the second reaction, isn't it? H dot plus HBr, HBr plus H dot. Then here it is products will be H2 plus Br dot. Here the reactant is H2 plus Br dot, isn't it? So the reaction, the fourth reaction is just the reverse of the second reaction. Okay. So again we can write another characteristic property of the fourth reaction is that it is the fourth reaction, it is the reverse of the second reaction. And also usually it is a fast reaction. And also see here in the fourth, here what happens, the formation of HBr will be decreased, isn't it? That means here HBr is formed in the third step, and in the fourth step again that HBr is consumed by this H dot, isn't it? So what happens is that the formation of HBr is decreased in this particular stage. Okay, so at this stage the formed HBr, it will be combining with another H dot to form H2 plus Br dot. That means the product here will be hydrogen molecule plus bromine radical, isn't it? So the formation of HBr will be decreased at this step. So in the fourth step itself, the formation of HBr is also decreased. The formation of HBr decreases. Okay. Then the next one, that is the step 5. See, coming to step 5, two bromine radicals will be combining to form bromine molecule, isn't it? So here this bromine radicals, it will be accumulating at this stage, isn't it? At the fifth step, this bromine radical will be accumulating to form a bromine molecule, isn't it? So this fifth reaction, since it is a free radical reaction, what happens? The reaction will be very fast, or the reaction will be occurring readily. The reaction will be occurring readily. Okay. And also here bromine radical will be accumulating at this stage. Bromine atom will be accumulating at this stage. See here, what happens is that the quantum yield of this H2Br2 reaction, quantum yield, it is denoted by phi, isn't it? Quantum yield of H2Br2 reaction, it is very low. Okay, it is very low, that is about 0.01. Okay, the quantum yield, it is about 0.01. And also here also, as in the general case, we can say that as temperature increases, the rate of the reaction also increases for this particular H2Br2 reaction. Okay, as temperature increases, rate of the reaction also increases. Okay, and also now we can go through some of the differences between H2Cl2 reaction and H2Br2 reaction. Okay, H2Cl2, here it is H2Br2. Okay. Only two differences are there between this H2Cl2 and H2Br2. The first one, H2Cl2, we had already seen it is an exothermic reaction, isn't it? But in the case of H2Br2, it is an endothermic reaction. And again, what about the quantum yield of H2Br2? It is 0.01, isn't it? H2Br2, it is about 0.01. That means the quantum yield, it is very low for H2Br2. But in the case of this H2Cl2, the quantum yield is very high. The quantum yield is very high. Okay, so these are the two differences between H2Cl2 as well as H2Br2 reaction. So this is the kinetics of H2Br2 reaction. Hope you understood this H2Br2 reaction. And then the next one, the next title, that is the, hope you write this also. Then the next one, that is the secondary photochemical processes. Secondary photochemical process. Secondary photochemical process. Secondary photochemical process. See here, in the secondary photochemical process, we have seen an atom when it is irradiated, or when it absorbs a photon. What happens? The atom, sometimes it will be in the ground state, it will be moving to the excited state by absorbing this particular amount of energy, isn't it? It will be going to the excited state, and again what happens is that this atom, it will be emitting some radiation, and this radiation, this emitted radiation, it will be having sometimes a same frequency, or it will be having a different frequency. The emitted radiation, it will be having the same frequency or a different frequency. Okay, so if the emitted radiation, it is having the same frequency, we can say that this particular phenomenon, we can call it as the fluorescence. It is called as fluorescence and phosphorescence. Okay, if the emitted radiation, if it is having the same frequency, we can call it as fluorescence as well as phosphorescence. But here the difference between this fluorescence and phosphorescence is that in the case of fluorescence, when the source is removed, what happens? It will be stop emitting. Okay, it will be when the exciting source is removed, it will be stopping this light emission. Okay, when the source of when the exciting source is removed, when the exciting source is removed, it will stop emitting radiation. But here in the case of phosphorescence, it will persist for some more period. Okay, in phosphorescence, it will be lasting for some more time. Okay, so that is the difference between fluorescence and phosphorescence. So here, when an atom it reaches to the excited state, and after reaching the excited state, it emits radiation to go back to the ground state or the lower energy states. And while emitting radiation, this radiation will be having same or different frequency, and such radiations or the phenomenon, that particular phenomenon, we can call it as the fluorescence or phosphorescence. Okay, fluorescence will be stopped when the exciting source is removed, but phosphorescence, it persists for some more time even when the exciting source is removed. Okay, then we can go through in detail of these two cases, that is the fluorescence. First one, that is fluorescence, and the second one, that is phosphorescence. Okay, so first one, fluorescence. See, suppose an atom A, when it is irradiated, it will be excited. That means it will be absorbing this photon and it will be excited. That means A star. Okay, so the atom, it is excited and it will be going to the higher energy state. See here, this excited molecule, this activated molecule, either it can undergo collision with some other molecule and can form products, isn't it? That is one chance. It can undergo collision and then it can form products, or otherwise it will be emitting radiation, and the transitions will be going on there, and it will be going to the lower energy state, or it will be going to the ground state. Okay, it will be moving to the lower energy state. By emitting radiation, it will be moving to the lower energy state. Okay, so here this radiations, usually they will be, so here these radiations are emitted while moving to the lower energy state. Okay, so we can write this A star again giving A1 star plus H nu 1. It will be emitting radiation to form this A1 star. Okay, again this A1 star will be emitting radiation. Again it is going to the next energy state, lower energy state, giving H nu 2. So here we can see the radiations with different frequencies, or the molecule will be having somewhat lower energy, that is they are moving to the lower energy state, that is from A star it will be moving to A1 star then to A2 star, isn't it, by emitting a certain different amount of radiations, isn't it. So here the radiations of different frequency are emitted. The radiations of different frequency are emitted. So radiations of the same, we can say that it will be emitting radiations of same or different frequency. That phenomenon we can call it as the fluorescence as well as phosphorescence. Okay, so here the radiations of different frequency are emitted, and that we can call it as the phenomenon, that is fluorescence. Okay, fluorescence. So here the molecule will be moving to the lower energy states by emitting radiations of certain frequencies or different frequencies, and that phenomenon we can call it as fluorescence. Okay, fluorescence. So examples of some of the compounds which are showing fluorescence are that is first one, that is eosin. Okay, eosin. Then the next one, that is fluorescein. Eosin, then fluorescein, then chlorophyll. Okay, these are some of the substances which exhibits this property fluorescence. So if fluorescence is asked, you have to write this much points. Okay, so here the radiation emitted, see the frequency of the emitted radiation, it will be less than the incident radiation. Okay, the frequency of the emitted radiation will be less than the frequency of the incident radiation. Okay, so then here what happens is that the absorbing molecule is it will be going from the transitions will be happening from the highest vibrational energy level, isn't it? From the highest vibrational energy level to the lowest energy states. So what happens, corresponding radiations are emitted with different frequencies, and therefore the phenomenon, it is called as fluorescence. Okay, and again the next point is that, see, atoms usually, the next term, that is the resonance fluorescence. Resonance fluorescence. Next term, that is resonance fluorescence. Sometimes it may be asked in the B part, for 2 marks it will be asked. So usually atoms will not be having any vibrational energy. There will not be any vibrational energy for atoms. So when it moves from the excited state, once it reaches to the excited state, it has to become stable, no? So it will be going to the ground state. So while moving to the ground state, it will be emitting radiations for moving to the ground state, isn't it? So if the radiation emitted if the emitted radiation, or if the radiation emitted, it will be the same, the frequency will be the same, then we can call it as resonance fluorescence. Okay, so if it is emitting radiation of exact frequency, if it is emitting radiation of exact frequency, we can call it as the resonance fluorescence. Same frequency as the incident radiation, then we can call it as the resonance fluorescence. Okay, so one of the example given in your textbook is when mercury vapors, when it is irradiated with a light of wavelength 253.7 nanometer. The wavelength, it is 253.7 nanometer. What happens is that this mercury vapors will be excited. That means excited state means it will be moving to Hg star. Okay, then this Hg star will be moving to the ground state. Ground state means it will be back to Hg. Okay, and also some radiation will be emitted during this process. Okay, the radiation will be emitted, and this radiation will be having the same frequency. Okay, this radiation will be the emitted radiation will be having the same frequency as it is absorbed. Okay, so that phenomenon we can call it as the resonance fluorescence. Okay, hope you understood that this resonance fluorescence. Then the next one, that is the sensitized fluorescence. Next is sensitized fluorescence. Sensitized fluorescence. See here, when this mercury vapor, when it is irradiated with a light of wavelength 253.7 nanometer, and along with that some trace amount of silver or thallium or lead or zinc, when it is mixed with this mercury vapors, see what happens is that these particular metals or these particular elements will not absorb this light radiation. Okay, only mercury has the power has the capacity to absorb this particular amount of light radiation. These substances is not having the capacity to absorb this particular radiation. So what happens is that this mercury will be absorbing this particular amount of energy, and it will be moving to the excited state. Okay, that means mercury will be moving to the excited state, or it will get activated. That means it will becomes Hg star. Okay, so what happens is that some amount of energy which is absorbed by this Hg star, it will be transferred to any of these elements. It can be sometimes if it is mixed with silver, what happens, some amount of energy will be transferred to this silver. Okay, so what happens, this silver, a sufficient amount of energy is transferred to silver, since silver cannot directly absorb this light radiation. Okay, so this energy will be transferred to silver, and then what happens is that silver will be moving to the excited state by emitting by absorbing this amount of energy. Okay, So it will be moving to the excited state, and then after moving to the excited state, what happens? It will be emitting radiation. It has to go back to the ground state, isn't it? Or it has to go back to the lower energy states. So for moving to the lower energy states, what happens? It will be emitting radiation and thus reaching the lower energy states. Okay. The silver will be reaching the lower energy states, and this phenomenon we can call it as sensitized fluorescence. Okay, sensitized fluorescence. That means this particular substance, it cannot absorb this light radiation directly. So with the help of some another element, it will be absorbing energy. That means this mercury will be directly absorbing the light radiation, will be moving to the excited state. That excited molecule will be transferring some amount of energy to these particular elements, to any of these elements. Thus it will be showing sensitized fluorescence. Okay. Then one more term, that is the quenching of fluorescence. Quenching of fluorescence. Quenching of fluorescence. See, quenching of fluorescence means when a photochemically excited atom, that means we can write it as a star, isn't it? X star, we can denote it as X star. When this photochemically excited atom collides with another atom, what happens is that the intensity of the fluorescence, the intensity of that particular radiation, it will be diminished. So by collision, what happens? Some amount of energy will be transferred, and the intensity of the fluorescence of the emitting radiation will be diminished. Okay, intensity will be diminished. Intensity will be diminished. Intensity of the fluorescence will be diminished. So this phenomenon, that is called as the quenching of fluorescence. Quenching, the word meaning means prevention. Okay. So when a photochemically excited atom, when it collides with another atom, the intensity of fluorescence will be diminished. This phenomenon, it is called as quenching of fluorescence. So here what happens is that the transfer of energy takes place from the excited atom to the colliding atom. Okay, the transfer of energy, this excited atom has got some amount of energy, it will be transferred to the colliding atom. So what happens? The intensity of this colliding atom, or the intensity of fluorescence, will be diminished. Okay, so that is the term quenching of fluorescence. So this much is about this fluorescence. So we have seen fluorescence, its definition for fluorescence. Then 2-3 terms are there, that is resonance fluorescence, sensitized fluorescence, and quenching of fluorescence. Then the next one, that is the phosphorescence. Phosphorescence. See here, phosphorescence means here deactivation of electrons takes place. Deactivation of electrons, deactivation of the excited state takes place. Deactivation of the excited state takes place. That means here when a substance absorbs a particular amount of energy, it will be excited to a higher energy state, isn't it? And again, gradually when the incident radiation is cut off, what happens? When the incident radiation is cut off, it will be emitting light even after this incident radiation is cut off. Okay, this here what in this case, in the case of phosphorescence, a substance will be absorbing a particular radiation, or it will be irradiated, then it will be going to the excited state, and again even after while going to the excited state, in order to go back to the ground state, it will be emitting some radiations, and it is a slow process. And during this process, when the incident radiation is cut off, what happens? It will be emitting light even after this incident radiation is cut off. Okay, so this phenomenon we can call it as phosphorescence. Okay, the phenomenon, it is called as phosphorescence. So here it emits light. It emits light even after the incident radiation is cut off. even after the incident radiation is cut off. Okay, so this phenomenon, it is called as the phosphorescence. So here it is the deactivation of the excited state. So this usually this phosphorescence, it is caused by UV and visible radiations. Phosphorescence is caused by UV and visible radiations. In zinc sulfide, normally it will be occurring. Then alkaline earth sulfides, etc. This phosphorescence phenomena will be occurring. Okay. Then one more point is there. See here, what happens is that in this phenomenon of phosphorescence, usually it will be emitting light energy of a longer wavelength. It emits light energy of longer wavelength. It emits light energy of longer wavelength. And also here what happens is that when the excited molecule, it passes through a series of energy states. See here, so many energy states are there. Suppose this is the ground state, this is the next higher energy state, like that it goes on. See, if the molecule, it is present here, what happens after the incident radiation is cut off, it will be coming down to the next energy state. So what happens is that this particular molecule, it will be trapped here, isn't it? And after that, then again it will be moving to the next lower energy state. Again it will be trapped there. Okay, then it will be moving to the next energy state or the ground state. Then again it will be trapped there. So the molecule will be entrapped at some energy states. Okay, this particular molecule, which is at the fourth energy level, it will be trapped at third, second, as well as the first energy levels, isn't it? So what happens is that since the molecule is trapped, what happens, this light emission will be persisting. Since the molecule is trapped at these stages, this emission of light will be persisting even after the removal of the light source. Okay, so this phenomenon, we can otherwise call it as delayed fluorescence. Okay, the phenomenon, we can otherwise call it as delayed fluorescence. So that is the next term, delayed fluorescence. Okay, so here delayed fluorescence occurs because the molecule, while traveling through a series of energy levels or series of transition states, it gets trapped, and therefore delayed fluorescence occur. Okay, so this much is about your topic. Hope I had completed your portions. If there is any doubt, you can ask me. Okay, so thank you for now. Bye.